Welcome to Efiwe, excellence without stress.
Hello guys, welcome to Efiwe, excellence without stress. And in today's study we are going to be considering metals and their compounds. Before we get into it, let's briefly look into the periodic table. So you will notice that in this periodic table it is actually made up of different elements and the arrangement is based on their increasing atomic numbers. However, you will notice that on this far left side where you have the purple coloration, you have your metals. These are your S block metals. Then coming to the center, you have your transition metals. Here you have your lanthanide and actinide series, and then you will notice that this more or less orange colored part is the remaining metals you have. These green parts are not metals, they are your metalloids. And then you have your other non-metals as these ones on this side. So the metals here are indicated by the purple color, this light blue color, and then this orange color basically. So with that said, let's move ahead. The first group of metals we're going to be talking about are your alkali metals. They are basically elements including lithium, sodium, potassium, rubidium, cesium, and francium. The occurrence: despite their close chemical similarities, the elements do not occur together, mainly because their ions are of different sizes. Sodium is the most abundant of alkali metals, followed by potassium, rubidium, lithium, and cesium. Francium is intensely radioactive and very rare. Lithium is the 35th most abundant element by weight and is mainly obtained as a silicate. Minerals such as your spodumene and your lepidolite are actually compounds that you could find lithium in. Sodium and potassium are the 7th and 8th most abundant elements by weight in the earth's crust. The largest source of sodium is rock salt, which is sodium chloride. Various salts including sodium chloride and the rest of them, your borax, your salt, pets, and sodium sulfate are basically other salts of obtaining sodium from other compounds. Potassium occurs mainly as deposits of potassium chloride known as sylvite, a mixture of potassium chloride and sodium chloride, and double salts such as we have in this case. There is no convenient source of rubidium and only one of cesium, and these elements are obtained as byproduct from lithium processing. All of the elements heavier than bismuth with atomic number of 83 are basically radioactive. Hence, since francium has the atomic number of 89, it is also going to be radioactive, and it has a short lifespan or half-life of 21 minutes. It does not occur appreciably in nature. Extraction of the metals. The metals may all be isolated by electrolysis, so take note of that your group 1 metals are extracted by electrolysis of their fused salt. Usually they are fused halide, often with impurities added to lower the melting point. So the main reason you introduce impurities to the halide of the metals salt you want to extract is basically to reduce the melting point. Sodium is made by electrolysis of a molten mixture of about 40% sodium chloride and 60% calcium chloride in Downs cell. So the impurity here is calcium chloride. This mixture melts at about 600 degrees Celsius compared with when you are melting only pure NaCl. When you melt only pure NaCl, it is going to melt at 803 degrees Celsius. The small amount of calcium formed during the electrolysis is insoluble in the liquid sodium and dissolves in this particular mixture. So it's important that you take note of that. There are 3 advantages to electrolyzing, that is probably introducing these impurities. First off is that it lowers the melting point, so reduces the fuel bill. The lower temperature results in a lower vapor pressure for sodium, which is important as sodium vapor ignites in air. At lower temperature, the liberated sodium metal does not dissolve in the melt, and this is also important because you need to obtain the sodium. Because if it dissolves, it will short circuit the electrode and thus prevent further electrolysis. A down cell comprises of a cylindrical steel vessel lined with fire bricks measuring about 2.5 meters in height and 1.5 meters in diameter. The anode is a graphite rod in the middle and is surrounded by cast steel cathode. A metal gauze screen separates the two electrodes and prevents sodium formed at the cathode from recombining with the chlorine produced at the anode. So basically that you would have that once you are dealing with electrolysis, it's a major method for extracting your group 1 metals, of which sodium is the most abundant. The molten sodium rises as it is less dense than the electrolyte and is collected in an inverted trough and removed and packed into steel drums. A similar cell can be used to obtain potassium by electrolyzing fused potassium chloride. However, the cell must be operated at a higher temperature because the melting point of potassium chloride is higher, and this results in the vaporization of the liberated potassium. Since sodium is readily available, the modern method is to reduce molten potassium chloride with sodium vapor at 850 degrees Celsius in a large fractionating tower. This would eventually give potassium of 99.5% purity. Okay, so talking about the reactions that basically occur, you find out that all of these substances would react with water to give hydrogen gas and the metal hydroxide. They also react with oxygen in air to give either an oxide, peroxide, or superoxide, depending on the metal. So have that in mind that anytime a group 1 metal reacts with water, it is going to produce the hydroxide of the metal and also give off hydrogen gas. These metals almost always form ions with a positive charge. This is simply because they have one valence electron in their outermost shell. Hence, the first ionization energy would be smaller and easily kick out that one electron. So just have that in mind that once you are dealing with your group 1 metals, they are going to be positive because they have only one valence electron, which is eventually given off to form their corresponding univalent cations. Most of the alkali metals glow with a characteristic color when placed in flame. Lithium is crimson, sodium gives off an intense yellow color, potassium is lilac, rubidium is red violet, and cesium gives off blue light. So this is more or less a flame test for these metals. The electronic structure. Group 1 elements all have one valence electron in their outer orbital, which is an s electron, and this occupies a spherical orbital. The single valence electron is a long distance from the nucleus. It's only weakly held and is readily removed. In contrast, the remaining electrons are closer to the nucleus and more tightly held and are removed only with great difficulty. Because of similarities in the electronic structures of these elements, there are many similarities in their chemical behavior. Talking about the size of the atoms and ions, group 1 atoms are the largest in their period in the periodic table. When the outer electron is removed to give a positive ion, the size decreases considerably. So that's why we would say that the cations of group 1 metals are basically less in size than their corresponding neutral atoms. There are two reasons for this. The outermost shell electrons has been completely removed. Having removed an electron, the positive charge on the nucleus is now greater than the charge on the remaining electron. So each of the remaining electrons is attracted more strongly towards the nucleus. This reduces the size further. Positive ions are always smaller than their parent atoms. Even so, the ions are very large and they increase in size from lithium to francium as extra shells of electrons are added. The lithium is much smaller than other ions. For this reason, lithium only mixes with sodium above at a temperature of 380 degrees, and it is immiscible with metals like potassium, rubidium, and cesium when they are molten. In contrast, the other metals, sodium, potassium, rubidium, and cesium, are miscible with each other in all proportions. Density. The atoms are large, so group 1 elements have remarkably low densities. The first ionization energies for the atoms in this group are appreciably lower than those of any other group in the periodic table. The atoms are very large, so the outer electrons are only held weakly by the nucleus. Hence, the amount of energy needed to remove the outer electrons is not very large. On descending the group from lithium to sodium to potassium to rubidium to cesium, the size of the atom increases. The outermost electrons become less strongly held, so the ionization energy decreases. Electronegativity values for the elements in this group are very small. In fact, the smallest value of any element. Thus, when these elements react with elements to form compounds, a large electronegativity difference between the two atoms is probable and ionic bonds are formed. So anytime you have a large difference in electronegativity, the implication is that you are likely going to have an ionic compound formed between the two elements combined. Chemical properties of some of the metals, or some reactions basically carried out by these metals in group 1. So we have that every one of them reacts with water to give a hydroxide of the metal and hydrogen gas. The hydroxides are the strongest bases known. So hydroxides of group 1 metals are the strongest bases you can think of, with excess dioxygen. So lithium basically forms a monoxide, and then sodium to a small extent might also form a monoxide. But then a peroxide is formed by sodium and to a small extent by lithium. On the other hand, potassium forms a superoxide. So you would also note that superoxides are formed by potassium, rubidium, and cesium. If they are to react with hydrogen, they are going to form hydrides. On the other hand, if they are to react with nitrogen, only lithium would form a nitride, and then the rest of them would react with phosphorus to form phosphides. So have that in mind. All group 1 metals react with hydrogen to form hydrides, only lithium reacts with nitrogen to form nitrides, and then finally all group 1 metals react with phosphorus to form phosphides. With this said, we would also go to the fact that all the metals, when they react with sulfides, sulfur, they form sulfides, they also react with halogens to form halides, and basically that. All metals form fluorides, chlorides, bromides, and iodides when they react with your halogens, and also all of them react with ammonia to form your amides. What then are the uses of some of these metals? Lithium is used to make electrochemical cells, both primary and secondary batteries. Lithium is used in the lubricants in glass industries and in alloys of lead, aluminium, and magnesium to make them less dense and stronger. What then are the uses of sodium? Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Sodium has many biological uses like nerve signal transmission in the body. Sodium nitrite is a practical ingredient in gunpowder. The pulp and paper industry uses large amount of sodium hydroxide, sodium carbonate, and sodium sulfate. Sodium carbonate is also used by power companies to absorb sulfur dioxide, a serious pollutant from smokestack gases, your locomotive chimneys or ship chimneys. Sodium carbonate is also used in glass industry and in detergent industry. Sodium chloride is used in foods and to soften water. Sodium bicarbonate, on the other hand, is used as making baking soda and is used in the food industry as well. Potassium is essential as an element for life. Roughly 95% of potassium compounds are basically used as fertilizers for plants. Potassium hydroxide is used in detergents. Potassium chlorate is used in explosives. Potassium carbonate is used in ceramics, color TV tubes, and fluorescent light tubes. Potassium bromide is used in the photography industry. Then we consider the rubidium and cesium. Rubidium is used almost exclusively for research, but cesium is used in special glasses and radiation detection equipment. Then we go into group 2 metals, which are your alkaline earth metals. The elements include beryllium, magnesium, calcium, strontium, barium, and radium. Alkaline earth metals make up the second group of the periodic table, which implies that they are likely to have, or they are all going to have, 2 electrons in their outermost shell. This family includes the aforementioned elements. The metals are silver and soft, much like the alkaline metals of group 1. Each alkaline earth metal, as I mentioned, has 2 electrons in the outermost shell, and they will easily give these 2 electrons up to form cations. These metals become increasingly more reactive as you go down the group. So which means if we are considering these reactions, you will find out that strontium should be more reactive than calcium, and calcium should be more reactive than magnesium because reactivity increases down the group. So with that said, this is concurrent to the general periodic trend that reactivity increases down the group of your metals. The group 2 elements show the same trend in properties as we are observed in group 1. However, beryllium stands apart from the rest of the group and differs much more from them than lithium does from the rest of group 1. The main reason for this is that beryllium atom and beryllium ion are both extremely small, and the relative increase in size of beryllium ion to magnesium ion is 4 times greater than the increase between lithium and sodium. Beryllium and barium compounds are very toxic. So basically, because of these size differences, beryllium in most cases would act different or very much different than most of the other elements in its group. As I mentioned, beryllium and barium compounds are all very toxic, so please try to avoid them. The elements form a well-graded series of highly reactive metals but are less reactive than group 1 metals. They are typically divalent and generally form colorless ionic compounds. The oxides and hydroxides are less basic than those of group 1, hence their oxo salts, which include your carbonate, sulfate, nitrate salts, are less stable to heat. What this means is that when you expose these salts to heat, they can decompose. In the case of their carbonate salts will decompose to give the oxides of the metals and carbon 4 oxide. So let's continue. These metals are all found in the Earth's crust, but not in the elemental form, as they are very reactive. Instead, they are widely distributed in rock structures. Beryllium, like its neighbors, lithium and boron, is relatively not very abundant in the Earth's crust. And basically, it is found in small quantities as silicate minerals of burial. Magnesium is the 6th most abundant element in the Earth's crust. The main mineral in which magnesium is found are your caronelites, which include a mixture of potassium chloride, magnesium chloride, which is hydrated, your magnesite, and your dolomite. Calcium is the 5th most abundant element in the Earth's crust, hence the 3rd most abundant metal after aluminium and iron. So aluminium is the 1st, iron is the 2nd, calcium is the 3rd most abundant metal. Calcium is found in gypsum, which is your hydrated calcium sulfide, your anhydrite, your fluorite, your apatite, and your limestone. There are 2 crystalline forms of calcium carbonate, which include your calcite and your aragonite. Strontium, on the other hand, and barium are much less abundant but are well known because they occur as concentrated ore, which are easy to extract. When you say something occurs as a concentrated ore, it means that most of the ore does not have a lot of impurities, basically that. They are respectively the 15th and 14th elements in abundance. Strontium is mined as calcite, which is SrSO4, and strontianite. Barium is mined as barytes. Radium is extremely scarce and is radioactive. It was first isolated by Pierre and Maria Curie by processing many tons of uranium ore pitch blende. Of the elements in group, only magnesium is produced on a large scale. It is extracted from seawater by the addition of calcium hydroxide, which precipitates out the less soluble magnesium hydroxide. This hydroxide is then converted to chloride, which is electrolyzed in a downcell to extract magnesium metal. So have that in mind, that your group 2 metals are also extracted by electrolysis. The metals of this group are not easy to produce by chemical reduction because they are themselves strong reducing agents and they react with carbon to form carbides. They are strongly electropositive and react with water, and so aqueous solutions cannot be used for displacing them with another metal or for electrolytic production. All the metals can be obtained by electrolysis of their fused chlorides, with sodium chloride added to lower the melting point, although strontium and barium tend to form colloidal suspensions. So mind you that once you are dealing with group 1 metals and group 2 metals, the form of extraction that occurs is extraction by electrolysis of their fused salts or fused halides. Properties of the elements. Alkaline earth metals are silver white, lustrous, and relatively soft. Their physical properties when compared with those of group 1 metals show that they have substantially higher melting point, boiling points, enthalpy of fusion, and vaporization. They have 2 valency electrons, which may participate in metallic bonding compared with one electron from group 1 metal. This is actually what accounts for the higher melting point. Consequently, group 2 metals are harder, have higher cohesive energy, and much higher melting points and boiling points than group 1 elements. The melting points do not vary regularly, mainly because the metals adopt different crystal structures. So take note of that. This can be understood in terms of the size factor and the fact that 2 valency electrons per atom are now available for bonding. Again, beryllium is notable in melting more than 1100 degrees Celsius above lithium, and being nearly 3.5 times as dense, its enthalpy of fusion is more than 5 times that of lithium. When we talk about the size of atoms and ions, it is basically the same thing as that of group 1. Moving ahead, if we then are to consider the different reactions that occur in your group 2 elements, magnesium is more electropositive than the amphoteric beryllium and reacts more readily with most of the non-metals. It ignites with halogens, particularly when they are moist, to give magnesium halide, and bonds with dazzling brilliance in air to give your magnesium oxide and your magnesium nitride. It also reacts directly with other elements in group 5 and group 6 when heated, and even forms magnesium hydride with hydrogen at 570 degrees Celsius and 200 atm. Steam produces magnesium oxide or magnesium hydroxide plus hydrogen, and ammonia reacts at elevated temperature to give magnesium nitride. The higher alkyne earth metals, calcium, strontium, and barium, including your radium, react even more readily with non-metals and give direct formation of nitrides. So, other products are similar, though the hydrides are more stable and carbides less stable than those of your beryllium and magnesium. So the same reactions that magnesium occurs is the same thing that these other ones will go through. There is also a tendency previously noted for the alkali metals to form peroxides of increasing stability in addition to the normal oxides. Some reactions of group 2 metals: magnesium reacts with hot water, and calcium, strontium, and barium can react rapidly with cold water. You will find that they react to form normal oxides. Every member in this group, when it reacts with oxygen, will form a normal oxide. With excess dioxygen, barium can form a peroxide. On the other hand, you will notice that all of these metals in group 2 will react with hydrogen to form metallic hydrides, and all of them will react with nitrogen, and all of them will react with nitrogen at a very high temperature to form metallic nitrides. If they happen to react with phosphorus, all metals would form phosphite at high temperature. All of these metals will react with sulfur, selenium, and tellurium to form your sulfides, selenite, and tellurides. Whenever these metals react with halogens, they form your halides, basically fluorides, chlorides, bromides. You would also notice that they can react with ammonia to form the amides at a very high temperature. Let's consider their hydroxides. Beryllium hydroxide is amphoteric. When you say something is amphoteric, it means that it can react with both an acid and a base to form salt and water. But the hydroxides of magnesium, calcium, strontium, and barium are basic. The basic strength increases from magnesium to barium, and group 2 shows the usual trend that basic properties increases on descending down a group. The sulfate salts. The solubility of sulfates in water decreases down the group. That is to say, beryllium sulfate is more soluble than magnesium sulfate, which is more soluble than calcium sulfate, and calcium sulfate is more soluble than strontium sulfate, and then you have that strontium sulfate is more soluble than barium. So the implication is that beryllium sulfate and magnesium sulfate are soluble. However, calcium sulfate is sparingly soluble, and the rest of them are virtually insoluble. The significantly higher solubilities of beryllium sulfate and magnesium sulfate are due to the high enthalpy of solvation of smaller magnesium ion and beryllium ions. The sulfates all decompose on heating to give the oxides of sulfur. Magnesium sulfate and calcium sulfate cause permanent hardness in water, while the presence of magnesium bicarbonate and calcium bicarbonate causes temporal hardness in water. If you now consider the hydrides of your group 2 elements, the elements magnesium, calcium, strontium, and barium all react with hydrogen to form hydrides. Beryllium hydride is difficult to prepare and is less stable than the others. Hydrides are all reducing agents and are hydrolyzed by water and dilute acids with evolution of hydrogen gas. The nitrides of this salt, the nitrides of group 2 elements basically are formed by burning nitrogen in the metal. So the implication is that, in contrast to group 1, where lithium is the only one that can form a nitride, all other group 2 elements can actually react to form nitrides. All nitrides are all crystalline solids which decompose on heating and react with water, liberating ammonia and forming either the metal oxide or hydroxide. Let's now consider the uses. In its elemental form, magnesium is used for structural purposes in car engines, pencil sharpeners, and many electronic devices, such as laptops and cell phones. In a biological sense, magnesium is vital to the body's health. A magnesium ion is a component of every cell type. Calcium metal is used to make alloys with aluminium for bearing. It is used in iron and steel industry to control carbon in cast iron and as a scavenger for phosphorus, oxygen, and sulfur. Chemically, calcium hydride is sometimes used as a source of hydrogen. Radium was used for radiotherapy treatment of cancer at one time. Other forms of radiations are now used. Now let's consider your group 4 metals. The elements of group 4 include carbon, silicon, germanium, tin, and lead. However, the only metals amongst them are tin and lead. The occurrence of these elements basically is that elements of the group 4 in the periodic table are well known, with exception of germanium. Carbon is the 17th and silicon is the second most abundant element by weight. Germanium minerals are very rare. Germanium usually occurs as traces in ores of other metals and in coal, but it is not well known. The abundance of tin and lead are comparatively low. They occur as concentrated ores which are easy to extract. Now, the only important ore of tin is cassiterite, and that is tin 4 oxide. So take note of that. Tin 4 oxide is reduced to the metal using carbon at 1200 to 1300 degrees Celsius in an electric furnace. The product often contains traces of iron, which makes the metal hard. Iron is removed by blowing air through the molten solution to oxidize the iron to iron 2 oxide, which then floats to the surface and eventually is passed out. The main oxide of lead is galena, and it is your lead 2 sulfide. There are two methods of extracting the element. First method is by roasting it in air to give lead 2 oxide, and then reduce the lead 2 oxide using coke or carbon 2 oxide in a blast furnace. So you have that the reaction is going to be, first you roast in air, where the galena, which is the lead 2 sulfide, is converted to lead 2 oxide. And then after that, you now introduce your reducing agents to remove the oxygen. So lead 2 sulfide is partially oxidized by heating and then blowing through air. The air is turned off. After some time, the heating continues and then the mixture undergoes self-reduction. This is basically the second method of producing your lead from galena. The group 4 elements are found in the p block, which means that tin and lead would have their electronic configuration ending with p. Each of these elements has only 2 electrons in its outermost p block or outermost p orbital, with electronic configuration of ns2 np2. The group 4a elements tend to adopt oxidation states of +4, and for the heavier elements +2. So once the elements are heavier, they have +2, but for the lighter elements, they basically have +4. With that said, we move on. Members of this group conform well to general periodic trends. The atomic radii increases down the group and ionization energy decreases. Metallic properties increase down the group. Carbon and silicon are non-metals. Germanium has some metallic properties. Tin and lead are the actual metals. The elements in these groups are relatively unreactive, but reactivity increases down the group. M2 oxidation state becomes increasingly stable on descending down the group. Lead often appears more noble or unreactive than expected from its standard electrode potential of minus 0.13 volts. The unreactiveness is partly due to the surface coating of the oxide. So the reason you find out that lead appears to be unreactive is that when lead reacts or is exposed to the atmosphere, it produces an unreactive oxide which covers the lead and protects it from further breakdown. Carbon, silicon, and germanium are unaffected by water. However, tin reacts with steam to give tin 4 oxide and hydrogen. Lead does not react with water in any form, probably because of its protective oxide film. Tin is used for electroplating steel to make tin plates and alloys. Lead is used to make lead/acid storage batteries. Lead is used as a protective shielding against X-rays and radiations from nuclear reactors. Now let's consider the chemical reactivities and trends. First of all is that tin is notably more reactive and electropositive than germanium. It is stable towards water and air at ordinary temperature. However, tin tends to react with steam to produce tin 4 oxide and hydrogen gas. On heating in air, tin would give tin 4 oxide. Dilute hydrochloric acid and your tetraosulfate 6 acid show little or no reaction with tin. On the other hand, when you have your dilute nitric acid, it produces tin nitrate and ammonium nitrate. Tin basically reacts with conc HCl to yield tin chloride and hydrogen, while on the other hand, it reacts with conc H2SO4 to form tin sulfate with sulfur 4 oxide gas. The occurrence of tin 2 compounds in these reactions is notable. So take note of that these particular products that are formed when you have conc HCl reacting with tin is a tin 2 compound, as well as in the case of sulfuric acid. Mind you that tin is more stable as a +4 oxidation state, while lead is more stable as a +2 oxidation state. Occurrence of tin 2 compounds in these reactions is notable, as I mentioned. By contrast, hot aqueous alkalis yields hydroxostannate 4 compounds. That is to say, when tin reacts with alkalis in hot aqueous solutions, it tends to form these stannate 4 compounds and give off hydrogen gas. It reacts readily with chlorine and bromine in the cold, fluorine and iodine on warming to give your tin 4 halides. It also reacts vigorously with heated sulfur and selenium to form tin 2 and tin 4 chalcogenides. Now, basically your chalcogenides are basically your elements of your chalcogenes, which are your group 6 elements. If we then talk about selenium, selenium basically reacts with tin to give tin 2 selenium. Now we would consider the chemical properties of lead. The first one is that finely divided lead powder is pyrophoric. When you say something is pyrophoric, it simply means that it ignites in air, it burns in air. Reactivity is greatly diminished by formation of a thin, coherent protective layer of insoluble lead oxide or oxocarbonate, sulfate, or chloride. So as I said, lead is more or less seen as very stable simply because it forms a protective thin layer over its surface, hence stopping further reactions with lead. If you have fluorine reacting with lead, it is going to give your lead 2 fluoride. Chlorine would give lead 2 chloride on heating, and molten lead would basically react with any chalcogen to give your lead sulfide, your lead selenide, and your lead terinide. Now let's consider the ores of lead and tin and their uses. Cassiterite, as I mentioned earlier, which is tin 4 oxide, is the main ore of tin and is reduced with carbon to form tin. Galena basically is your lead 2 sulfide and is roasted in air and eventually reduced to your lead using your carbon. The alloys of tin include your solder, your bronze, your pelter, and then you find out that this is an important use of tin. Lead is primarily used in your storage batteries and also in your radiation shields. Let's now get into transition elements. The elements in the middle of the periodic table, that is the D block, are basically classified as transition elements. However, it is important to note that they are basically elements with partially filled d orbitals. They serve as a bridge or transition between metallic elements of group 1 and 2 and the elements of group 3 to 8. They are all metals, hence they are called transition metals. Transition metals may be divided into main transition metals found in the D block and the lanthanide and actinide series found in the F block. The lanthanide and actinide series are sometimes known as the inner transition metals because they have atomic numbers that fall between the first and second elements in the last two periods of the transition metals, or as rare earth elements. A transition metal is one with an incompletely filled d or f orbital in any of its commonly occurring oxidation state. Scandium and zinc do not count as transition metals, even though they are numbered in the D block. The reason is because scandium ion has no d electron, as you can see in the configuration, and then zinc ion has a completely filled d orbital. So if it is going to be referred to as a transition element, especially if it is a main transition metal, it is going to be classified on the basis of partially filled d orbital. In contrast, copper forms two ions, copper 1 and then the more common one, which is your copper 2. So we have that the labelings are there. Your D block elements are basically everything here, but then you have your lanthanide and actinide series, which are your F block elements. Now let's get into the general properties of transition elements. They are all metals, they are all malleable and ductile. They conduct heat and electricity and they form positive ions. What then is the difference between transition metals and then the normal metals? Most of them are harder. They are more brittle and have higher melting points and boiling points. They exhibit multiple oxidation states, except a few of them like your zinc. Their ions and compounds are usually colored and they form many complex ions. Many of them are also paramagnetic. The other differences include that your transition metals are more electronegative than your main group metals, hence are more likely to form covalent compounds. Transition metals form salts in which negative ions balance the charges on the positive ions, and basically this is unlike your normal metals or unlike your main group metals. But they are more likely than your main group metals to form complexes. As you can see, they have the ability to form complex ions. So if we are to consider electronic configuration of some of the transition metals, the first 10 transition metals are the most important transition metals, and they include scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Notice something, that in the case of your copper and your chromium, instead of having 2 electrons in the 4s orbitals, it preferably takes 1. Why? Because you will find out that additional stability is associated with half-filled or fully filled orbitals, and that is why you have a variance in the electronic configuration of chromium and copper. Moving ahead, the oxidation states. Sulfur, nitrogen, and chlorine, as well as lead and tin, show variable oxidation states in their compounds. However, transition metals exhibit a wide range of oxidation states. Most common amongst them are +2, +3, and +4. Transition metals also form compounds with low oxidation states, with neutral ligands, example like your carbon monoxide, your alkenes, your arenes, and the rest of them. The study of the low oxidation compounds is included with organometallic chemistry. So, the compounds in their highest oxidation states are often powerful oxidizing agents. Things like you have your tetraoxomanganate 7 ion and your heptaoxodichromate 6 ion. The very next property of a transition metals is that they form colored compounds, unlike your normal metals, basically. And you will notice that there is a wide range of colors that can be formed by such transition metals. You can notice this is chromium 3 with the blue color, iron 2 with the light green color, your cobalt with the red color, and the rest of them. When you talk about magnetism, properties can be correlated with either number of the d electrons or number of unpaired electrons. If you have unpaired electrons, it basically leads to the phenomenon known as paramagnetism. basically a situation where you have that these elements become attracted to the poles of the magnet. If all electrons are paired, this is what we refer to as diamagnetism. And then in this case, you will have that these elements will begin to repel the magnet. The next property of transition metals is basically the ability to form complex ions. Transition metals plus a ligand will basically lead to the formation of a complex ion. As you can see, the ligands include water, ammonia, and your chloride ion. So once a transition metal combines with this particular substance, they basically form a coordinate covalent bond, and this leads to the formation of these complexes. The next thing to note is that transition metals are basically very good catalysts. For instance, you will notice that your titanium chloride is a good catalyst in the production of polyethylene. Your vanadium 5 chloride is basically used in contact process for production of sulfuric acid. Your manganese 4 oxide is a catalyst for decomposition of potassium chlorate to give oxygen. Iron serves as a catalyst in Haber process in the making of ammonia,